Inside modern hardware, arithmetic modules are indispensable. Many applications such as artificial intelligence, high-performance computing, and high-frequency trading cannot be achieved without high-speed computing modules. According to von Neumann architecture, the arithmetic logic unit is the most important part of the CPU. It is the brain of the computer, responsible for performing a variety of arithmetic and logical operations. Generally, a simple ALU contains 2 operand inputs and 1 operator output. The operator input use different code to represent different functions. There are many operations in one ALU, including the addition, subtraction, multiplier, division, power, square rooting, and trigonometric functions. According to the performance analysis of a deep learning model, the addition and multiplication accounts for over 99% time for one AI model inference. Thus, experts mostly consider optimizing these 2 operations, which have the greatest impact on hardware performance improvement. Therefore, researchers have studied optimizing adders and multipliers since the birth of computers. Before introducing the optimization method, we should understand the basic implementation of adders and multipliers. In the 1-bit addition of binary, we have 2 1-bit inputs. 0 plus 0 equals 0, 1 plus 0, or 0 plus 1 equal 1, while 1 plus 1 equals 0 with 1 carry. According to the truth table, the sum and the carry bit can be implemented by a different OR gate and an AND gate separately. After all, this circuit is called a half adder because it has 2 inputs A and B without the carry bit. If the inputs are more than 1 bit, we will use the full adder, which has an extra carry bit C propagated from the lower bit. According to the truth table, the full adder can be achieved by cascading 2 half adders and 1 extra OR gate. When having half adders and full adders, we can connect them together to build adders with any bit length. The lowest bit A0 and B0 are added by a half adder. Then, the bit A1, B1, and the carry bit are added together by 1 full adder, and the following bit are also added like this. However, the carry should be passed from the lowest bit to the highest bit, leading to the serial computing. Therefore, the computation time for addition increases linearly with the number of bits. So can the arithmetic hardware compute the bits in the method of parallel instead to improve the efficiency? The answer is yes. One solution is the prefix adder, which compute the carry bits in parallel. There are many implements of prefix adder designed by previous researchers. Simply, the principle of the prefix adder is to parallelize the computation of some intermediate results for the final output. The intermediate results can be seen as signals representing a specific interval. Each interval contains 2 signal bits, a propagation bit P and a generation bit G. We use Pij and Gij to represent signals for the interval of bit I to bit j, such as P1, 5 and G3, 6. For the signal bits of length 1, the propagation bit and generation bit can be achieved by an AND gate and an XOR gate. Signal bits of longer intervals can be directly achieved by 2 consecutive subintervals. For example, interval 1, 2 can be got by 1, 1 and 2, 2. Similarly, interval 1, 5 can be achieved by interval 1, 2 and 3, 5. Finally, when we have all the interval signals from any bit to bit 0, we can get the results of adders. An interval can be used more than once. Thus, we use a hierarchy structure to demonstrate the merge process. If one interval is generated by 2 subintervals, then they're connected by edges. The structure is also called prefix tree. Different prefix will lead to different hardware performance. The main indicators used for scoring them are level and size, which determine the delay and area of adder. The level, the maximum height of the prefix tree. Higher level prefix adder will lead to higher delay. In this prefix tree, the level is 5. The size is the total number of the intervals. Larger size leads to the larger area usage of the adder. In this, the search space is extremely large. It increases exponentially with the number of input bits. We model the prefix adder search as a single-player game. It is very like a board game, and the intervals are stones. And the actions are adding and removing stones. Each action step will generate a new prefix adder structure. We use the Monte Carlo tree search to play the design game. Four steps are executed iteratively until finding the best adder. Our method can found the best 128-bit adders, surpassing the best results found a decade ago. From our simulation tests, we can decrease the delay and area of adder. Other than adders, the multiplier can also be optimized. For multiplier, it contains 3 parts. The compressor tree can also be improved. Simply, the compressor tree is to use to half adders and full adders to merge bits from partial products into few bits. The design of compressor tree is very like some match games. The game items are half adder and full adder. The bits at the same digit need to be matched by the items. So we model the compressor tree as the match game and using the reinforcement learning strategy to solve it. An agent are trained to select actions based on the current bits for maximizing the multiplier performance. For the multiplier design, we use a co-design strategy to optimize the compressor tree and the prefix adder back and forth, achieving the global optimal multiplier. Also, we verified that our designs can transfer to the advanced technology library without any adjustments. This validates the generalization of our approach across different technology nodes. In the future, we will optimize more kinds of arithmetic modules, such as exponentiation, logarithmic operation, trigonometric functions. Also, we will try to make a real chip, testing the performance of our designed modules on real applications.